All right, so, well, thanks for coming. And today, no jacket and tie. I mean, I'm probably the only person visiting Russia and complaining about the hot weather. So, okay, so today we are going to talk about control. And the presentation is essentially a trip in my research activity over the past 20 years. And I would like to start this trip with a sort of story, which is a very British story, and that sort of describe why I like very much this object that I've shown also on the other set of slides. Now, before we do this, I would like to give you a sort of overview of the talk. So we see on these slides a lot of different problems, and the longitude problem, which is associated with the clock that I've shown, a chemical process, this hurricane that we discussed the other day, a tokamak reactor, a lady swimming in a lake, Star Wars, the Eclipse aircraft that we have seen the other day, a viral infection, and the legend of Queen Dido of Carthage. So you would probably look at all these and say, well, okay, nice pictures, but what do they have in common? So what I would like to show in this hour and a half is that actually these pictures have a lot in common. So if you look at all these pictures and the problems which are associated with this picture in a proper way, you will see that there is a common denominator, which is the denominator of control and system theory. Now the talk is going to be slightly more technical than the other time, which means that we will have a few more equations showing up here and there, but everything is reasonably at a low level. So if you have an understanding of differential equation, of dynamical systems, of sets, you should be fine. Okay, now what is this British story that I want to use to start this talk? So we all know that if you want to find longitude at sea these days, it's extremely simple. We just pick the GPS and we know where we are. However, in 1707, we have 4 large British warships, and they were coming back from a battle against Spain, and they misjudged their longitude, and they ran aground on the island of Scilly. So the British were very happy because they had defeated the Spanish, but then all their fleets essentially was destroyed in the Isle of Scilly. And the government was so upset that they've offered £20,000, which is approximately £3 million of these days, to the first person that was able to measure accurately longitude at sea. Now, what is longitude? Well, we all know that approximately we can represent the Earth in this way, and we have lines that go from the North Pole to the South Pole, and then we have lines that I'm not showing that they sort of lies in this direction, so from the North Pole to the South Pole. Now, it's very easy to decide whether you're close to the North Pole or whether you're close to the South Pole, but it's impossible to decide on which of the meridian you are, because they're all the same. I mean, the fact that the zero meridian now goes through Greenwich is only a convention, but it could be anywhere else. And there were other conventions in the past. It could go through Paris, it could go through other places. So whether you are east or west of something is only a convention. So it really depends where you are. So the longitude is essentially the problem of finding where you are relative to your previous position, for example, and considering the lines that are cutting the globe from the North Pole to the South Pole. So how do you do that? Well, the simplest possible approach is the following. We know that approximately there is 1 rotation of the Earth per day, so 360 degrees per day, which is 15 degrees an hour. So time is longitude. So if I have something that moves and I can measure a difference in time, then I have a way of obtaining longitude from time. And so we could say in a very formal way that time gives a parametrization of what is a Riemannian manifold. We are not really interested in the details of this, of an object. The Earth, if you remove the North Pole and the South Pole, is like a sphere with 2 little holes, and this has the property that a Riemannian manifold should have. And then if we consider the projections of every point of the Earth along this line, you see all these points, they're all the same. So this is our projection. So we can use time to parameterize all these points. Okay, so this is at a distance of a certain amount of time, 1 hour from the other points. ahead or in the other direction, depending whether we are east or west. So this is a very simple way of parameterizing the problem. Now, of course, you're asking me what control has to do with this. Well, we'll come back to this in a minute. So if time parameterizes the longitude, we need a way to parameterize time, and we need a way to have something that gives us a good measure of time. Again, this is trivial these days, but it was not trivial in the 17th century. So if we have, for example, a dynamical system, we know that the dynamical system has trajectories which are parameterized by time. So a dynamical system is a very good object, but a dynamical system is not very useful because, for example, it exists in our computer or it exists somewhere. We want to be able to have a system that has periodic trajectories, because if we have a periodic trajectory, then we have a natural clock. And you see to the right that this is a very simple pendulum, and it was discovered by Galileo in 1602 that this is a very simple oscillator. It has very simple trajectories. These trajectories are periodic, so essentially you have a clock. So you go from the longitude problem to a clock in a very natural way. And the pendulum is described by this second-order differential equation. And of course, this is true if everything is ideal. So the second derivative of the angle is equal to gravity divided the length of the pendulum times the sinus of the angle. And the whole is equal to 0. So if you approximate this differential equation and you assume that you're doing small oscillation, you also know that the period of oscillation is proportional to 2 pi and the square root of L divided G. So again, you have a very simple clock. If you want to measure time, you can build a pendulum. You can decide what is L. You know approximately what is G. You do the square root, you multiply by 2 pi, and you have a clock. Now, if you have large oscillation, the situation is slightly different because you need the elliptic integrals, but again, it's not so important for our purposes. I mean, you can still parameterize time using a pendulum. So this is all very nice. So if we want to find longitude, we need just a pendulum. But this was known. The Vikings used to use this trick. In 1553, long time before the British fleet was stranded on the Isle of Scilly, Gemma Frisius described how you can build a pendulum to solve the longitude problems. The problem is that it's very easy to solve the longitude problem if you are at land, because you can move your pendulum, can be very, very careful in moving this pendulum, and then you can measure time in a very simple way and longitude. But what happens at sea? Well, at sea the situation is much more complicated because you have rough sea, you have lots of change in temperature, in humidity, in pressure. So this means that instead of having your very simple clock, you have something like a feedback system. The length of the clock is changing because temperature, this is, for example, composed of metal. You may have large temperature variations, and so this is changing. So the length is changing. There are some external signals, like the waves, which are affecting your pendulum. If you try to have a pendulum on a boat, even in a normal day, and you try to wait to see the oscillation, you will see that it doesn't do at all something like that. So you see that the idea of feedback, the idea of control is coming already in the picture. But in this case, the idea of feedback is not very good because the feedback is actually destroying periodicity of this pendulum. So what happens is that we have a very nice ideal object. Yes?
Excuse me, please, but why does the length depend on
time? Because if you have temperature variations, this is actually a very crucial problem. So if you have temperature variation, this is a rod of metal, and you may have little expansion of this. And so actually the solution of the problem relies on a way of constructing a pendulum which does not have variation in L. Okay? And of course, if you have variation in L, this differential equation is not precise anymore, so you need to have some term to the right-hand side which are describing the disturbances which are due to the time derivative of the length, which is sometimes, which is probably very small, and to other externals. So if we have a pendulum which is excited, so a pendulum at sea, you see that you have three possible periodic trajectories, and they don't look really like the periodic trajectory that we would expect from a normal pendulum. The situation is and then this is the tip of the pendulum. So you see that in the space of position and velocities, so angular position and velocities, you have very, very strange motions for the tip of the pendulum. So again, this is not a periodic motion, it's something that we cannot use in order to measure time. And the situation is even more complicated if the pendulum is vertically excited, so if you move it up and down like this. In this case, you have what is called the chaotic attractor. So you can generate in the space of theta and theta dot trajectories which are somewhat dense in the space of possible trajectories. And the three attractors that we have over there, they are somewhere embedded in this picture. So what happens is that we have a very nice object, a pendulum, a very simple object. We have a nice concept that is time is equal to longitude. But then if we have perturbation or variation, all this is completely useless. Okay, so we have to find a way to compensate for the effect of C, of temperature, and so on. Now, this type of pendulum has actually been studied by a Russian Nobel Prize, Kapitsa. He got a Nobel Prize not for work on mechanical system, but for superconductivity. And then he studied this particular pendulum, which is a vertically forced pendulum. You see, you have oscillation along the vertical, and then with the wheels that is just below, you can push it up and down. And so you can observe the type of strange behavior that we have seen. And now, a Kapitsa's pendulum clock is always faster than a clock with a fixed suspension. Okay, so this is a faster clock, and so the time that you measure is actually not a good estimate of the real time. So a pendulum alone is not adequate to measure time, and we need a feedback system, because feedback by itself is something that we use in order to remove to remove the effect of disturbances, or at least to attenuate the effect of disturbances. Of course, the person Harrison that solved this problem and that built this clock that I've shown you in the first slide didn't know anything about control. I mean, he was a very skilled man, but didn't know anything about control as we know it today, the idea of closing the loop. So he implemented control, he implemented feedback loop, but in a very ingenious way, in a mechanical type of way. So he implemented a set of mechanical objects that when put together, they were applying feedback to a normal pendulum. So the first invention was the so-called greedy-rom pendulum, and this does not change in length with temperature. So it was using zinc and iron, assembled in a special way that if some part of the pendulum is expanding, the other is contracting, and overall there is no change, no net change in the total length of the pendulum. The second interesting observation is that he had to have a way of stopping the pendulum. So suppose that you measure time with a pendulum that goes up, then you freeze for a second, and then it will go here, and then you freeze again, and then you go here, and then you freeze again. Why do you want to do this? You want to do this because you want sort of to synchronize this movement. You want to make sure that as you go from here to there is always the same time, and you want to avoid large oscillations, perturbation, and so on. And this is the second feedback loop that Harrison invented. As you see, it's a mechanical type of feedback. Once there is a movement, one of the two arms, it goes up and the other goes down, and so on. So there is feedback here. You see that you get information from one side that is transferred on the other side, but it's not feedback in an electronic point of view. It's not feedback of signals. It's feedback of forces, and it's not implemented with a computer. I mean, these days, we would just measure the angle over there, we'll feed this back into a computer, we will have a little motor on the other end, and we'll take an action. Okay? This is much more ingenious because you don't need all this equipment. You don't need much. Okay, the only thing that you need in order to have this work is a type of battery. Because you see that if you have a pendulum and you stop it, then you lose energy, you let it go, you stop it again. So you have a mechanism that will keep the energy going. So Harrison invented the so-called maintaining power, which is an alternative source of energy which drives the clock while it is being moved. The problem is that you cannot stop the pendulum and recharge the pendulum again, but you have to keep the pendulum going while you recharge, otherwise you lose time. Okay, so if we want to look at the closed loop system, Harrison put one of these clocks on a boat, and on a 2-month trip London to Jamaica, the feedback clock was 5 seconds long, which means that as you go from London to Jamaica, complete without no information on the longitude, it takes 2 months, and you only miss 5 seconds. I bet that nowadays clock, they will not be so precise. On the trip from London to Barbados, it was 39 seconds long. So this second attempt was not as good. You had an error of 10 miles in longitude. In the previous case, it was 1 nautical miles. But still, it was very outstanding in terms of performance. So the longitude problem was solved using a coordinate system. So we have decided that we have longitude, and longitude is time. So once we know that longitude is time, we go from a coordinate system to a dynamical system. And then we understand that there's a lot of perturbation acting on the system, so we require a feedback mechanism. And then, once we have the feedback mechanism, these days we would use sensors, actuators, computer to implement it. In the case of Harrison, we have to have hardware design of the controller, which means you have to come up with a design of pieces of metal such that the feedback controller was implemented. And this is extremely tricky. It's probably very easy today to synthesize an electrical circuit that achieves a certain goal, but if you want to design a mechanical circuit, a mechanical system that achieves a certain goal, this is extremely difficult because we don't have enough intuition for this particular type of system. Now, as an historical comment, Harrison needed 5 years to build the first chronometer, and 30 years and the help of King George in order to have the money of the prize, and actually half the money of the prize because they were not really happy to give the money of the prize to a person that was not even a member of the Royal Society. It was not a learned person. You see, it was a skilled person. Okay, now mechanically controlled systems. There's quite a lot of them in the history. So this is a Russian object. It's called the digesting duck, and this was developed just for fun. And so this is a duck which is composed actually of 2 mechanical systems, and one is moving the legs, and the other one, if you feed this duck with something, what happens is that whatever you give the duck is going to go inside, and then something happens, the leg will move, and you have the impression that the duck is digesting because something is coming out from the back of the duck. So, and this was all based again in a very simple construction of mechanical devices. But then again, you could say mechanical construction is obsolete. These days we have computer, we can implement with sensor, feedback, actuators, and so on. And this is not really true. Now, suppose that I want to design an object that provides a force which is proportional to relative acceleration between 2 points. Now, we all know that we can generate a force equal mass times acceleration, but then if instead of having one acceleration, we want to consider a device that generates a force which is proportional to relative acceleration, you see, you have 2 terminals, then this is much more complicated. Now, this device has been created just a few years ago, and it's called the inerter, and actually, this is a practical application of the inerter, and this is what are common suspension in Formula 1 cars. You may probably know that in Formula 1 cars is not allowed to use electronic suspension anymore. You cannot measure the displacement of the wheels. You can feed this information to a computer, and you cannot have an actuator that will fix the strength of your suspension, but you can have a mechanical implementation. So this is nothing else than the active suspension that we have in all our cars. In Formula 1, they cannot be implemented anymore, but you can implement them through this type of devices. So this device was developed at Cambridge University and has been used for the first time by McLaren Formula 1, and since then they spy on each other. Everyone has this device. It has a different name. It's not called inerter, but the original name is exactly this. Okay, now let's move from this type of historical description to a few interesting control problems that have practical applications today. So we start from a very simple problem, which is a classical optimization problem. So suppose that we are given a function and we want to maximize this function. So we all know, for example, if you want to reach the top of the mountain, that there is a shortest path to the top of the mountain, which is actually the path of the gradient. So you have to move along the trajectories of a dynamical system, which is the time derivative of your motion should be proportional to the derivative to the gradient of the function f, which means that you go on the steepest slope. So this is the shortest path. It may not be the most comfortable path, but it's the shortest path. And then if we have a very simple function like the one over there, you see that the red line, which is just visible, is describing the motion of this dynamical system. Now, optimization is something that we are solving every day. We all try to wake up as late as possible to be where we have to be in the morning at the right time. This is an optimization problem because we want to reduce travel time from home to work or to university or whatever. We want to maximize a lot of things in our life. So optimization is very important. But optimization in general is subject also to perturbation, to disturbance. In the example that I was discussing before, if we want to minimize travel time, there is traffic, there may be problem on the underground and so on, and we are not aware of this. So this means that when we want to minimize a function, we have to do this in a dynamic way. We have to be able to take decision in a dynamic way. We cannot just decide on a strategy initially and then go along this strategy, but we have to modify our strategy online. Now let's see how we can do this in a dynamic way. So suppose that I'm given this quadratic function. So this is still a static function, so it's something very simple to optimize. And you see that if x is equal to x star, the quadratic term disappears, and so I am at the top of the mountain. So in this case, the simple selection x equal to x star is going to give me the right answer to the optimization problem. But I need to know the structure of the function. Now, is there a way I can optimize this function without knowing the structure? So suppose that I give you x and you give me y, but you don't tell me anything from what is inside. Well, this is now a sort of system with input x and output y, and then the information y is fed through a low-pass filter. You multiply by sinus of omega t, you pick some value omega, you integrate the signal, you multiply by sinus of omega t again, and then you close the loop. Okay, so you can implement this in a very simple way. This is a low-pass filter, this is an integrator, and these are a couple of external signals. All quantities are positive because in this case we don't have any problem in defining closed-loop solutions. Now, what can we claim for this very strange object? Well, we can actually claim that y of t will be an oscillating signal, but will be very close to f star, which is the maximum value of the function. And so formally the lim sup as t goes to infinity of yt minus f star in absolute value is going to be smaller than some epsilon. And this epsilon is what we decide, how close we want to be to the top, and this is a function of all the parameters involved. So we have this parameter a, the parameter omega, k, and h. So we can tune this parameter in such a way that we achieve an almost optimization for our function, because we don't really reach the top, but we are very close to the top and we keep on moving. Why we keep on moving? For several reasons. The first reason is that we have no information on the function. We give an input and we have an output. Okay, so we have very little information on the function, so we have to keep on exploring the space. If this function changes with time, then we have to keep on exploring to satisfy our optimization goal. And the other reason is that the y is moving with time because we are injecting this periodic signal. And the idea of injecting periodic signal is that we are probing the space. We are looking in the positive direction when we have sinus of omega t, then sinus becomes negative, we look in the negative direction. And you see that if we forget for that signal for the time being, suppose this is a constant, you have a sinus, you integrate, you have a cosinus. This means that one is a derivative of the other. Okay, so we are considering the product of a signal with its derivative, which means that we are essentially implementing the gradient method, but we are implementing this online. And we are implementing this method with a closed loop system that doesn't know anything about the function. You don't need to know anything about the function. So you can extend this to dynamical system. So suppose that now you have a dynamical system, strongly stable. This means that if I apply constant input, I should get constant output. And so I can define a steady state map. If I apply a constant u, x is going to converge to some value that I call xu, and I have an output which is h as a function of xu and u. And then I want to maximize the output of this system. So in the case of the travel time from one place to another place, this is a dynamical problem because there's a lot of disturbances, there are a lot of things that change as time goes by, but we want to minimize the total travel time. So we repeat exactly what we have done before. So we pick our dynamical system with all these nice properties, and we close the loop pretty much as we have done before. So we take the output of the signal, we let it through this filter, we multiply by sinus omega, we integrate, we add a sinus of omega. So we are essentially implementing the same loop on a different object. Before it was a function, and now it is a dynamical system. Now we can show that the average of the output of the system, which is what we measure over there, converges to the maximum of h xu of u. So we are able to obtain the maximum performance with respect to this particular output without any knowledge of the dynamics of the system. And this is very useful because if you have a process that is producing something, typically you don't have a very accurate model for this process, but you would like to maximize the yield. You would like to maximize the quality of what you produce, and so you can achieve this with this loop, which is called an extremum seeking loop. You seek the extremum, you seek the maximum in this particular example of the input-output map of a dynamical system. Now, it is extremely important to observe that the optimization of the output map is achieved with no knowledge of the system, simply by feedback. So the feedback is able to learn what is the maximum, so what is the input that has to be applied to the system in order to maximize the output function. So there is no information on the system on the structure of F and H. You just have to have some general information. For example, you need to know that you have some stability properties and so on, but this, for example, you can assess with experiment. There's no analytic expression needed for the system that you're studying. Now, there are a couple of very interesting applications that I worked out of this principle. So the first one is an application to a so-called waste-to-energy process. This is a very, very complicated process in which waste is essentially burned. And as you burn waste with a lot of constraint, because you have to reduce pollution, you have to make sure that what you burn actually is, you produce ashes, and these ashes can be disposed, and you want to reduce the size of what you burn. So you have a lot of environmental constraint. And the other issue is that if you burn environmentally hazardous components at a certain temperature, then you transform them in harmless compounds that you can, for example, deposit in landfill. Now, what happens is that the whole goal of this process is to burn waste, so to reduce the size of waste. However, doing this only for reducing the size of waste is not a good idea. So you produce a lot of heat, and so you would like to use this heat in order to produce energy. And the way you do this, you produce steam, and then you use a normal turbine and you produce energy. So the idea is that you have a process that is actually very simple. It's a very slow process. I mean, you put waste inside, you burn the waste, it takes a couple of hours typically, you produce heat, you send this heat to a heat exchanger, you produce steam, and from that you produce energy. You want to maximize the energy that you produce. So that's why this is called waste to energy. Okay, so this is a very complex process. So you have a lot of control parameters, which is the flow mass of the waste, the speed of the grates where the waste is moved when you burn. You have the air that is injected into the system. You have the temperature of the air, the pressure of the air. And typically you want to make sure that the gases that you produce, they have a specific amount of oxygen, which is exactly the same amount of oxygen that is in the air. Okay, so you want to have exactly the same proportion of oxygen. And then you want to regulate the flow rate of the steam because you want to produce electricity. So in the slides you see all the blocks which are describing the interaction between the various sub-processes in this very complicated process. However, we're not really interested in the details of the process, but still we want to optimize the operation of the process. So the goal is to maximize the amount of waste that we burn, that we treat. We want to maximize steam production, and we want to minimize air pollutant emission, despite variability of the waste, because we have no information on what is inside the waste. It's typically domestic waste, but it could be composed of a lot of things. Now, we know that the process has some strong stability properties. If you put waste inside, it will burn them and you get something out, as a well-defined steady-state map, and is essentially driven by piecewise constant disturbances, which are the disturbances composed by the waste, because you put some tons of waste there, and these are going to stay there for a couple of hours. Then after a couple of hours, you put some more waste, and you go in this way. So all the technical assumptions that we need to use extremum seeking control are actually satisfied, even if we don't know much about the structure of the process. So we now implement a control algorithm which has two loops. In the first loop, we set temperatures of the piles, so temperature inside the chamber that is wasting, and the oxygen and the waste throughput. So we apply this so-called feedback linearizing controller in order to make sure that all these parameters are set. And then we have a second loop, which is composed by the steam generation. So you measure steam, and then you close the extremum seeking loop. This means that you achieve all your goal: oxygen, waste throughput, temperature inside the chambers. On top of this, you maximize the steam that you produce. And so some data. To the right, we have that as a function of the temperature, you see that you have a map of the amount of steam that you produce, and typically you would like to use your turbine around the maximum, which is approximately this 38 line here. Okay, so this is the point where you want. And typically, so this means that your extremum seeking algorithm, starting from some temperature, should move close to that point. The problem is that this graph is changing with time because the waste is changing with time. And so the steam that you produce is going up and down close to the 38 value. And this is a graph over approximately 10, 20, 30 hours. Okay, so a bit more of a day. So the goal here is to maximize the performance of this plant without having precise information on the internal behavior of the plant, and we achieve this with extremum seeking. Another application of extremum seeking, which is very popular these days. Now, this should have been written tokamak in Cyrillic, and probably well, I don't know. Look nice on my slides. I should have made a mistake later on. Okay, is correct? Okay, right. So this is a device which confines plasma into a magnetic field and is used for fusion. So if you want to have a fusion device to produce electricity, this is the simplest possible object that you can think of. So the plasma is an electrical conductor and can be heated by a current. So the most popular way of heating current is using a radio frequency wave, which is generated by an antenna, and then you radiate the plasma with this antenna. And there is a picture to the right. Now the problem, as you all know, whenever you have transmission of waves of electrical, of electrical waves, or electromagnetic waves, then if you don't have coupling, then all the waves that you send to the plasma will come back, and rather than heating the plasma, you will be heating your antenna. So what happens is that you have two decision variables, which are your frequency and polarization. You have your radio frequency antenna and the plasma. And then you have a variable which describes the coupling. So you want to make sure that the radio frequency heating is efficient only if this coupling is maximized. So again, you can implement this extremum seeking algorithm in a way that the coupling is maximized. So you measure information on the plasma. Essentially, you measure the amount of energy that is sent back by the plasma, and then you try to reduce this amount of energy. Otherwise, the system will not work properly because the antenna will essentially irradiate itself using the returning waves. Okay, now we move to another application of control, which starts again with a little story. Now, it should have been nonlinear H infinity, and I'm sure that again in the slides is there, probably with the projector doesn't work, control, and there is a story of a lady in the lake. Now, so we have a lady that is swimming in the lake, and a man that doesn't know how to swim and would like to intercept the lady. So the only way that he could achieve this goal is to run along the shore and wait for the lady to touch the shore. And of course, the lady wants to escape from this situation. So if she's not intercepted at the time when she reaches the shore, she wins the game. Otherwise, if she intercepted, the game is won by the man. So how can we formalize this? I'm a control engineer, so I always have in mind this type of block. Okay, so I have this system, is a dynamical system. The lady is swimming in the lake. And then the man can take decision. He can decide in which direction to run and with what speed. And similarly, the lady, she has decision variable. She can decide in which direction to swim and with what speed. The man is taking some observation. The lady is taking some observation. Who is going to win this game? You see that you have two opponents. This is a typical game. If you play chess, you would like to win. Your friend or the person that is playing with you would like to win. So you have two competing goals. Okay, and this is pretty much the same situation. In chess, it's not really a continuous dynamical system because you have a finite number of possibilities and you have a time. Okay, so it's a discrete time system because you have like a clock which is given by each move, right? Not really by the external clock. In this case, it's a continuous system because the man could run continuously, the lady could swim continuously. So the man has a strategy and the lady has a strategy, and we assume that they're both very smart. So the lady would probably going to take the best possible strategy, and the man is going to take the best possible strategy. So let's see where this is going to go. So we have now two opposing players, and this could be the lady and the man, but it could be in chess, black and white. You have a differential game, which is called the evasion game in this particular example. Now, in the case of chess, this is not really differential game, but is a difference game. And then you have a cost that you want to maximize or you want to minimize. The lady would try to maximize the distance from the man, and the man would try to minimize this distance. So you see there is the same objective, but we would like to achieve different goals with this objective. And then we have a set of observation. I mean, the lady is swimming and she's looking around, and the man is looking in the lake. So how do we model this situation? Well, we have a differential equation here that describes the man running, the lady swimming. We have the distance, the performance variable, z. We have what we observe, y. And the whole problem is to minimize with respect to u. U is the lady. U is the man, wants to minimize. W is the lady, so you want to maximize. So you have a minimizer, you have a maximizer. When you play chess, also there is a minimizer and a maximizer. You try to maximize your, the number of pieces that you win, and the other person will try to minimize. And you assume that you're both very smart in doing this. You are both playing in an optimal way. And then you have decision variable. You have disturbances which are acting on the system. W is the strategy of the maximizer. U is the strategy of the minimizer. Then you have the goal Z and what you measure Y. Now, the goal is to find a strategy for the nice player. In this case, we are siding with the lady, using available information to minimize this cost J. And we are assuming that the bad player plays in an optimal way. So the man is very, very smart. So we have to outsmart the man in this particular game. Okay, so you can actually show that this is a feedback problem. So you see and you decide. Okay, so the lady cannot just say, I swim in that direction, and then she blindly swim in that direction because she loses the game. Okay, so she has to see and take a decision. So she has to find the feedback strategy. But now this is a very tricky problem. Okay, so let's try to simplify the problem and look at the picture. So the two players aim at opposite goals. You want to minimize or maximize. The maximizer is playing in an optimal way. So if we look at this function, you see in this direction, you go uphill, you are maximizing. In this direction, you go downhill. Now we assume that the man is playing optimal. So he's playing, if I'm here at this point, if I'm here at this point, over there, and so on and so on. So in order to make sure that this man will not outsmart the lady, then we have to find what is called the saddle point. So the maximizer cannot do any better without taking any risk. And similarly for the minimizer. This means that we have a saddle point where the minimizer can do the best, is taking the best possible strategy, which is under the assumption that the maximizer is also playing optimally. Okay? So from a technical point of view, you can actually show that in this particular case, you can swap the max and min sign in this optimization problem. And this means that the optimal feedback, also from a theoretical point of view, is indeed a state feedback. So you need to measure all the data, position and speed of all opponents in order to find a solution. Now this is a very nice story, but what has got to do with engineering and with control? Okay, so how do we solve this problem? Because this is, we're interested in solving this problem. So we assume that U is playing the best possible strategy, W is playing the worst possible strategy, so we can bias the input signal in this way. And then we have to find the optimal strategy. So what we do, we have some observation, and out of this observation we estimate the worst case. So we try to estimate the worst case scenario for the player that we would like to outsmart. And then we close the loop with the best estimated strategy. So we play a worst case game. We are assuming that our opponent is very smart, so we cannot make any mistake. We cannot be, we have to be very smart. So we don't have to make mistakes, and so we take a worst case scenario, and then we apply the best estimated strategy. In this way, the lady is going to win the game. Now, back to engineering. Is this any application? Well, an application that I worked out a few years ago is the following. So suppose that you have a chemical semi-batch reaction. A semi-batch reaction means that part of the, if you pick a Coca-Cola can, closed is a batch reaction. You leave it there for 50 years, something is going to change, but there is no action from the external world. A semi-batch reaction means that there's a lot of stuff inside this can, but you put something in at some rate because you want to change the behavior of this. Okay, so it's semi-batch because you put something in, you don't take anything out. Otherwise, it would be a continuous reaction. Okay, so this semi-batch reaction is very simple. You want to add B, and so the goal is to convert A, adding B, into C. So if I add all B at the very beginning, I put all B, salt for example, and I put it at the very beginning, this is not a very good idea because you see that B and B together will combine to create D, and I don't want to create D, I want to create C. Okay, so I have to give to this reaction a bit of B time by time in such a way that B will combine with A to produce C, but will not combine with itself to produce D, which is something that I don't want. So adding everything at the beginning is suboptimal. So the real reaction actually is also subject to perturbation. So A can be transformed into some other compound, B can be transformed in some other compound, and so on. So what we want actually, we want to maximize the production of C while minimizing the production of dt. We are not interested in D at some final time t, and all these additional compounds, E1, E2, and E3, we don't want them. So you see that this is a typical Ladyman scenario where we have to use B in a smart way to maximize C, and at the same time we need to minimize a lot of other objects. So this problem can be formulated mathematically pretty much as the problem that we have seen before, and you can get a solution to this problem which has actually engineering relevance. Okay, now let's move again to another problem. And as you've seen so far, I would like to give an historical flavor to all these problems. So this is a legend of Dido. So she was escaping from her brother, and she reached North Africa. This was several years before Christ. Actually, I don't remember precisely that. So she was given by the local king as much land as she could enclose with the hide of a bull. Okay, so this person was not really very generous because the hide of a bull is a couple of square meters. But Queen Dido was very smart. She cut the hide, so she made tiny little threads, and then she solved the isoperimetric problem. Of course, she didn't even know what the isoperimetric problem is. Well, the problem is that if you cut an hide and you try to enclose an area with the hide, you can take several decisions. You can pick this area, you can pick this area, you can pick this one and this one. But since this is going to be your city, you want to maximize the area. Okay? So she was smart enough to find the right solution to the maximization of the area enclosed by a perimeter of fixed given length. And so she solved the isoperimetric problem. She proved the isoperimetric inequality. Of course, she didn't know Green's theorem. She didn't know optimal control, but she solved an optimal control problem. Okay? So we all know now that among all closed curves in a plane of given fixed length, the one that is the problem of finding the one that maximizes the enclosed area is equivalent to the following problem. So among all closed curves in the plane enclosing an area, we want to find the one which is minimizing the perimeter. So maximizing the area or minimizing the perimeters are exactly the same problem. Now, if you do this together with Green's theorem, which is essentially helping you to exchange some terms in the integral, you end up with a set of differential equations and a minimization problem. You don't have a min-max problem, but only a minimization problem. So the integral is the perimeter of your area. X dot and y dots, they describe a dynamical system, which is the velocities that you take along the perimeter, and u and v, so u and v are the velocity and x and y's are the position. So you want to have a closed form, so x at time 0 and x at time 1 should be 0 because you want to go back, and similarly for y. So Dido's problem can be posed in this way. So we have this, which is, as you see, the isoperimetric system. And this is a very interesting system because if I take a jumping robot, so this is a very simple robot with one leg that will jump like this, and while in midair will reorient, and then write the differential equation, and you have exactly the same differential equation. So while Dido's problem is not very interesting today, jumping robot is much more interesting today because we can think of it as a very simple example of a running robot, if then you start adding two legs. But what is even more interesting, if I change coordinates, and I write the differential equation of this object, which is a mobile robot, I obtain exactly Dido's problem. So changing coordinates, redefining some variable, these equations and these equations are the same, and they describe the motion of this robot. Now, if I want to do robot control, I have to deal with these equations here. And these equations actually are very tricky. We will see in a minute why they are very tricky, and we already discussed this during the previous session. So, okay, suppose now that I have a mobile robot and I have a target position and orientation. My decision variable are the forward speed v, the angular speed omega, so how fast I go backward or forward, how fast I rotate left and right, and x, y, and theta are the position of the robot in the plane and the orientation of the robot in the plane. So the idea is that I would like to find a feedback function such that, two feedback functions, such that the robot will go from one point to a final point. So we would like to implement a feedback loop. We measure x, y, theta, we have some controllers, and then we find v and omega as a function of x, y, and t. So we've seen this picture already, and what this picture has told us, that for some initial configuration there are two natural trajectories. So the functions v and omega have to be discontinuous functions. So this is a very tricky problem in control because you have a sort of indecision. Have you ever driven a trolley at the supermarket and then you have two cash points in front of you where you can pay? So you're driving the trolley and you are precisely in between and you have to decide whether to go right or left. I mean, if there is no queue, this problem has no obvious decision. I mean, right and left, they're exactly the same. So this type of problem, so you have to take a decision which has nothing to do with feedback, has nothing to do with your observation of the problem. Because going right and left is exactly the same. There's no queue right, there's no queue left. You are exactly in the middle, and so you could go both ways. Okay, so in this case, you have a discontinuous feedback because there is an idea of decision in this feedback. Oops. Sorry. How do we study discontinuous feedback? We want to remove discontinuity, and this can be done actually in a very, very simple way, in a very systematic way. So we want to find a way in which we have a coordinate system, for example, a description of this ball, and we want to break the symmetry. You see that this circle is symmetric in all directions, whereas we would like to find a coordinate transformation that transforms this set into something which is, for example, very long in one direction, and it still looks like a circle in the other direction. Now, this is called the sigma process and has been widely studied in dynamical system theory. So it's a coordinate system in which small displacements near a point are going to give you a great change in coordinates in the other space. You see that in this direction, I'm not doing anything special. So if I move along this line, I move along this line. Whereas if I move in this direction, there is a big difference, because if I do a small step in this direction, I'm probably going to do a huge step in that direction. So I'm now breaking the symmetries. I'm distinguishing between left and right. Okay, so how do we use this for the mobile robot? We have our mobile robot, we apply the sigma process, so we break the symmetry. In a sense, if you have your two cache points and you have your trolley, you decide that you don't look left. Okay, you just look right. So as far as you are concerned, there is only one cache. Okay, then you apply the sigma process, you close the loop, you have your controller, you apply the inverse of the sigma process, which is called the anti-sigma process, and then from this point to that point, you have a system where there is no discontinuity. Okay, so you apply at the input and at the output of your system, where you have this possibility of indecision, because you could go left and right, you apply these two objects that are going to break the symmetry. It's like there is now a wall in between and you are on one side of the wall. You have already taken a decision. So the problem now is a very simple problem, because you have destroyed this possibility of indecision. So we have seen these pictures already, and essentially we have the fire truck. This is the kinematic description, and these are the differential equations. If you look at the first three differential equations, they pretty much look like the same differential equation of the robot. Yes, these three one. But then you have a lot of other equations, because you have more control here and you have other angles. Okay, but what happens is that you can control this using this idea of a sigma process and anti-sigma process in order to break the symmetry. Okay, so we have seen how the motion of this robot. Okay, now the next part. So Star Wars. So again, you know, this is not really an historic story, but it's also a very interesting story. So you may all be aware of the program that was run in the US when Reagan was president. They want to develop this Star Wars scheme where there were satellites in orbit with lasers, and the lasers were supposed to destroy enemy missiles and so on. This actually was a fake program, because they didn't have, and we still don't have lasers which are so precise, so strong, that from outer space they can destroy a missile that is flying in the atmosphere. Okay? But interestingly enough, we will see that the people that have participated in this, they have now developed a company that does a sort of Star Wars at a completely different level. I'm sure you are curious at this stage, because what sort of Star Wars can we do with lasers and missiles and so on? Okay, now, the problem is we have a flying object, we have data on the screen, so we have a 3D object, and we have two-dimensional data, and we would like to reconstruct the depth. Now, you have two possibilities. The object that is flying is a commercial aircraft, so you know what it's doing, or is an enemy missile, you don't know what it's doing. Okay, so the motion parameters may be known or may be unknown. Of course, if they are unknown, the situation is slightly more complicated. Okay, again, you have a problem and you have to go to the bare properties of the problem. So the problem lives in what is called the projective space, because we have this point living in the dimension 3, we have the monitor of our computer, and so what we see the projection of this object on the computer. So you see that if we have good coordinate system, essentially we only have to find the depth. The x and y on the screen, we know precisely what they are, but we have to know how far away this object is. Okay, so we have a dynamical system which describes the motion of the target. The motion parameters are this object A11, A12. They're not so important, they may change with time. If you have a commercial aircraft, you know what these numbers are. If you have an enemy missile, you don't know. And then you have some observation, and the observation are the y1 and y2 are the coordinates on the screen. You see, you measure y1, you measure y2. You don't measure x1, x2, and x3, okay? Because you don't know where the object is, you only measure the projection. So what you want to do, you want to find the depth of the object x3. So this is a very interesting problem, because the geometry is interesting. So if you define projective coordinates, so x1 over x3, x2 over x3, which are the coordinate on the screen, if you just do some trigonometry, you see immediately that this is the case, and then the inverse of the depth, then your dynamical system is written in these new coordinates, and there's a very nice structure, because you see that the inverse of the depth depends on the inverse of the depth and on the inverse on the depth square, and all the dots are function of y1 and y2, so functions that we know. And then we want to find another dynamical system with state theta, which is processing our available information, and is going to give us the inverse of the depth. It's easier to work with the inverse of the depth. So the idea is that you have a dynamical system with state x1, x2, x3, you measure y1 and y2, and this is fed into the system, and we want to find an estimate. Now, the filter have the property that as time goes by, y over x3 can be expressed. You see, there is this link. As time goes by, we can destroy this link. So we change coordinate. We define a new variable z that is essentially breaking this link. So now the problem is only to have z going to 0, because if z is equal to 0, y1 and y2 are going to give us immediately the depth. Okay? So again, the trick here is to change coordinates. Instead of looking at theta, we look at z. Z is a new variable with the property that z dot is a function of something that we observe times z, which means that if z is 0, z is going to be 0 forever. And so if we have a good observation, the object will keep on moving, but we can track the depth of the object. So the depth is known because z is vanishing. Again, you see that z is disappearing as time goes by. Z will go asymptotically to 0. Time is important here. We have a dynamical system. Okay, so Star Wars, the mosquito zapper. So I've already discussed malaria, and malaria is a problem that I like to study, and I have lots of collaboration with a biologist, a medical doctor, and we like to study the problem in an unconventional way. So malaria mosquitoes are responsible for 1 death a minute, so it's a very serious problem. Now, every possible way of eradicating malaria have not worked well, and so there is no viable vaccine. And we can discuss for a long time, if you want, why there are no viable vaccines. So rather than controlling malaria, we may want to control mosquitoes. Okay? So we use laser, we use target tracking, and we want to put laser at home that are going to kill all the mosquitoes that are flying. This looks pretty much like Star Wars. May I have the video, please? Sorry. No. Just click on the blue. Yeah. So there are mosquitoes flying in this box, and you can see the laser. Okay, the laser is trying to track the mosquitoes, and it's going to kill the mosquitoes. You see, one has just become green. And even if this is a low-power laser, actually after the laser has caught the mosquitoes, there's nothing remains of the mosquito. I mean, it's transformed into a little cloud of smoke. Okay, so, and actually it works. I mean, the laser is like 20 meters away and has no information on the way, okay, that's it, thank you, on the way the mosquitoes are flying, but is essentially killing the mosquitoes. Interestingly enough, this application has been developed by a subset of the person that were working at the Star Wars program during the Reagan era. Okay, now we go to the next chapter, which is adaptive control. Now, adaptive control is a very technical word, but let's see what it is in general, a way to understand adaptive control. So the idea of adaptive control is to continuously improve the way we make decisions. So the idea is that when we make decision, again, if we go back to the example that we take the underground to go from one place to another, something happens, we change decision on the basis of current information. So the reason that we want to change decision over time is that the environment changes, we have a lot of changes, and as time goes by, whatever is around us is changing, and so we have to learn from the past and take informed decision in the future. Decision taken now may not be optimal or may not be be good in a couple of hours. Okay, so how do we pose adaptive control? So we have a partially non-parameterized process. Again, you have a dynamical system, but now you have some parameters theta. These parameters theta are giving us all possibilities. Okay, as you change theta, you change your system. So the idea is that there are all sorts of possible ways to move from one place to another, and you can parameterize all of them with a parameter. Now, suppose that you know the parameter, you have information on the traffic, you have information on delays, you have information on strikes, you have all information that you want. So if all this information is available, then you apply a feedback to reach your goal, which depends on this information. But actually, you don't have all this information. Okay, these days, you have all the, all these electronic devices that are going to give you on-time information on traffic and so on, but still, you may not have all them online. So this is the ideal closed-loop system. You would like to take a decision on the basis of all the available information. Now, unfortunately, theta is not known, so we would like to find a learning mechanism. We would like to modify our feedback such that the feedback system behaves similarly to this one, as close as possible to this ideal closed-loop system. So what we do, we apply this feedback where we have a learning mechanism we find an estimate for the current traffic, the current delays, and so on, and we replace the theta that we have here with the estimate, with our best possible guess of the current situation. And so, how do we implement the learning tool? Well, the learning tool is implemented in a very simple way. We define a set that I call M, where I have complete knowledge of the situation as a function of a new parameter theta hat and of available information which are beta x. So on this set, theta, the set of unknown object, is known because I can write this equation as theta equal theta hat plus beta x. And then I define a distance to the set, which is z, and I'm asking myself how far away I am from this ideal set. Now, once I know how far away, I have to decide how theta hat is changed, because theta hat is my guess for the new decision. Okay, so the idea is that this surface is the ideal surface. If I'm here, I know everything, but actually I'm not there. But I would like all trajectories to move towards this ideal situation. I would like to learn as much as possible with time to go close to a situation where I know precisely what happens. So the learning mechanism in a mathematical perspective is described as attractivity of this set. So I would like to continuously improve knowledge and invariance. Once I have achieved perfect knowledge, I want to retain it. Once I know what the situation is, I want to retain it. This is similar to the target tracking case, where z was equal to 0. When I track the depth of the object, z is going to be 0 forever. Okay, so you don't want to lose information. You always want to continuously improve your knowledge. And then we apply a modified feedback mechanism where instead of using the actual state, the actual parameter theta, we use the available estimate. So we go back to this example. We now have a learning mechanism which is described in a much simpler way. It's a couple of differential equations and an output map. And then we change coordinates. You see, we break the loop and we replace this loop with something which is driving. And the reason that this is again a z variable is that the ingredients are essentially the same. So the idea is that we replace this loop with a new variable z, the distance to the manifold, which is telling us how our knowledge is progressing with time. And we would like z to go to 0, because if z goes to 0, this term disappears and we have perfect knowledge on our system. Okay, so we have improved our knowledge of the situation. So in the adaptive coordinate, there is no learning loop, and the controller is the ideal one, which is perturbed by a vanishing sea. So we have seen this application, and this has been applied to the problem of designing an autopilot for a class of aircraft without knowledge of aerodynamic parameters. So we have discussed this already. Okay, now, the next problem, as I've told you, I'm very interested in biological application of control, and again here there is an interesting story. So, an Italian mathematician, just after the First World War, was observing the number of fishes in the Adriatic Sea, and was impressed to see that the number of fishes has increased enormously. And so, of course, being a mathematician, he had to write differential equations, he had to see what these differential equations were describing, and so on. But you know, you can think in this way. During the First World War, all men were busy doing war, and so they were not fishing. So the fishes were very happy, and so there were lots of fishes in the Adriatic Sea. Now, you can actually formalize this in a simple possible scenario where you have a very simple ecosystem. So you have a desert island, you have rabbits and foxes. And the desert island is a very, it's a very good island for the rabbit because you have ample food supply, which means that also the foxes have ample food supply because the foxes are going to eat the rabbits and the rabbits are going to eat the food supply. Okay, so this is what is called a food chain, and Volterra studied this type of food chain, which are called prey-predator food chain. So there is a prey, which is the rabbit, and there is a predator, which is the fox. There is a prey, which are the fishes, and predator, which are fishermen in the Adriatic Sea. And so, in doing so, Volterra sets the basis for the understanding of viral infection. You see that the behavior is very interesting here. What happens? Since the rabbits can eat a lot, they have ample resources of food, they eat, they reproduce. I mean, if you have a small number of rabbits, you have a small number of foxes because they will starve. Now, as the rabbit reproduce, you have a large number of rabbits, and the foxes say, well, now there's a large number of rabbits, so we can reproduce, we can have a lot of foxes. And so what happens is that there is a peak in the foxes, and now all of a sudden there are too many foxes, and so they eat all the rabbits and they go down. But as you eat the rabbits, the fox will die because they have nothing else to eat. And the process continues. Okay, so the population will actually go up and down, because there is this mechanism, which is a two-way mechanism. You think that the foxes are eating the rabbits, but once they eat the rabbits, they have nothing left to eat. And so in principle, if they eat too much, they are going to sort of kill themselves. Okay, so this is the type of feedback mechanism. Now, why viral infection? So suppose that we have an infection, a virus, which is infecting CD4 T cells, which are a part of the immune system. And now, in this case, the cells become virus factory, and they make copies of the virus. So instead of helping the immune system, they're actually doing precisely the opposite. They are building virus. So the interaction between the virus and uninfected CD4 T cells is pretty much similar to foxes and rabbits. Okay? However, the environment is represented by the immune system, which implements a feedback mechanism. So we have pretty much the same situation where we have foxes and rabbits, and then instead of the desert island, the immune system. And the immune system has to act in such a way to make the rabbits smarter. Okay, so they have to run fast in such a way that the foxes, which are the viruses, are not going to catch them. Okay, so this is the type of feedback mechanism that the immune system is implementing. The immune system is always measuring number of virus and number of healthy cells, and is taking decision. Typically, is smart enough to take decision. If you have a cold, you wait a couple of days. Even if you don't do anything, the cold will go, because the immune system will apply a feedback mechanism which is going to kill all the foxes and let all rabbits be free. So suppose now that we have these ingredients, an infectious disease, the immune system, and now we need a drug acting on the system. Not all infectious disease will go without any drug. And so this means that we have another loop. And this second loop is a loop that is applied typically at the level of rabbits and foxes, because you can kill directly the virus and you cannot act directly on the immune system. So the problem in this type of structure is that we would like to find a therapy which boosts the response of the immune system, acting typically on the rabbits. We would like to make the rabbits stronger, smarter, faster, in order to escape the foxes. The problem is that although this mechanism of virus and uninfected cells is pretty much described by the prey-predator mechanism, the way drugs are affecting the body and the way the immune system is affecting the body is very unclear. So we don't really have a good model. We don't have very good measurement. We cannot have a computer that is measuring the level of viruses continuously, so we can measure once a week or once a month. And so we have a very difficult control problem, and the control action is also non-continuous. You take a pill a day, for example. Okay, now, the goal of the therapy is to enhance the immune response. You would like your immune system to be stronger so that you can react to the presence of virus. And now you can write a differential equation in this way. So W is one part of the immune system, and it's just the concentration of this object of the immune system. So you can actually integrate the differential equation. C in are the infected cells, and CH are the healthy cells. And you see that if I want to boost the response of the immune system, I have to make this as large as possible. So this is positive, and this is an exponential. To make it as large as possible, I have to make this FW positive. So the role of the therapy is to make sure that this quantity is positive, and the therapy can kill some of the infected cells or can give strength to some of the healthy cells. So these are the two mechanisms that we can use to improve the immune response. So this is a very simple planar problem. We have just two variables, and so we can actually solve the problem. We can find the therapy as a function of the number of infected cells and the number of healthy cells. And we actually worked out this therapy in a number of very interesting cases. For example, for serious infections like HIV-infected patients, of patients with particular type of cancer. So you can actually implement this type of therapy, and you can have very good responses. Now, from here to practice, there is a long way. You need to talk with the doctors, you need to have approval, and so on. But, we are working towards this. So this is a very interesting application of control that has an impact on solving, problems for serious types of. Okay, now this is almost the end of the talk, and I would like to give you a type of warning. So we have not really discussed too much the idea of stability and instability and so on, but if you have done anything in dynamical system theory, you would have heard this term, stability and instability. And now, the title of these last few slides is Respect the Unstable. Because if something is unstable, it may be very bad. It can be very damaging. Now, stability can be destroyed in several ways. Instability can be generated in several ways. In this case, we're talking about internal versus external stability, which means we have an object which is very nicely behaved, and then you have some perturbation which are acting on the object, which are destroying its dynamic behavior. So suppose that we have what is called the unforced Duffing oscillator. This is an oscillator that has an asymptotically stable trajectory. So if you solve this differential equation, you will have like the clock. Okay, it will go around, with a shape different from a clock. Now, if I have a forced Duffing oscillator, if I apply forcing to the right, then I have something much weirder. Okay, there is no clock anymore. Okay, so you have chaotic behavior. And then you could say, okay, fair enough, this is a mathematical curiosity. Is there any chance that we get this in real life? Well, first of all, the observation is that an external signal, this one, is altering or destroying the stability properties. Now, suppose that you're driving your bike on a very smooth surface, and all of a sudden you start having bumps, okay? And you don't know about these bumps. So this is your cosinus of omega t. It goes up and down, up and down. Depending on the speed and how skilled you are, you may be in trouble. But actually you may be in trouble even if you're very skilled. Look at this video. Can we start the video, please? So this is a TT Grand Prix at the Isle of Man. So this is a TT Grand Prix at the Isle of Man, and the driver is definitely a very skilled driver. So can you just click on the video? Yeah. So you see that the road has some bumps, and you have this accident. So the guy was not respecting the unstable. Nothing happened to the driver. Okay? But it's interesting, and it was going, I think, at like 180 miles an hour, so it was really fast. And everything was nice, but the bumps on the road were killing the stability properties of the system. Now, a second example of instability. We have a very nice closed-loop system, stable, well-behaved, no problem. But then typically in closed-loop system, we have limitation. So we have saturation. So we may have what are called saturation-induced instability. So this means that if we have limits on the control signal, all of a sudden a very nice behaved system may show a very undesired behavior. May I have the video again, please? No? Okay. Okay, so this is actually a test flight of a NASA aircraft. And you see, it's landing very, very nice and smooth. So, you have no problem in flying on this plane. But then, at some point where he's actually on the runway, the pilot takes a decision which is not very good, and the aileron are hitting saturation. And so you see what happens. You start getting oscillations, and of course you don't want to fly on this object, or at least not with this pilot. Okay, so again you have a situation where saturations are entering into the system, and the behavior is completely modified. Again, there was no accident here. The last example is again the tokamak example. So the plasma in the tokamak is rotating in this toroidal chamber and is naturally unstable. Now, several types of instability, you have several types of instability, but typically you have bubbles of plasma which are very hot, and they try to come up. Okay? Now, if they come up, the bubble of plasma will hit the chamber, and then they will destroy part of the chamber. And since these objects are worth several millions, well, probably hundreds of millions, you have to be very careful. So you have the shape of the plasma, which is what you have there, and then you have these bubbles of plasma which are going upwards. It's a bit strange, it looks like they're going against gravity, but the reason is that they sort of float into the plasma. So A feedback loop is dedicated to stabilization of this vertical position, and this is a safety critical loop. Okay, can we have a video? This is a real video of an experiment that we ran on a small fusion reactor close to Rome. I've told them to run the experiment while I was away from Rome, but so you can see now now this is dark, and the red shade is the shade of the plasma, and the white shades are these hot bubbles that are heating. You see? And they are hitting the boundary of this plasma. Okay, so this is an example of instability, and at some point you have to turn it off if your controller is not doing a good job, because otherwise you burn the whole device, and lots of people will not be very happy. Now, last example of instability, you would say, okay, being unstable is bad, so why do you want to build something that is not stable? Well, because you may want to have a very agile aircraft. If you have an unstable aircraft, this is a very agile aircraft. So both in the US and in Russia, you have this idea of building an aircraft with wings looking forward rather than backwards. And if you look at normal aircraft, then the flow of air goes from close to the body of the aircraft, and then it goes wide on the wing. And if you have this reverse situation, the flow of air is completely different. What happens is that this aircraft actually is unstable. So if you let it go, it will crash. Okay, so you will need the control system. The reason why you would like to have this aircraft is typically these are military aircraft, because you have increased maneuverability. They do not stall at large angle of attack, which means you can go very high and you don't stall. But of course you require very strong wings, you see, because they are somewhat suspended, the wing, and you require a very good control system. Okay, I think now it's time to conclude. And so I have a couple of quotations that I think are interesting. So the first one is, there is nothing more practical than a good theory, which is to say that we have to have a good understanding of the theory if we want to develop any practical application. So practical applications, they do not come anymore from ingenuity of the inventors, but you have to have a good theory. The second one is from Ernest Rutherford, and it doesn't seem to be a control type of quotation. So all physics is either impossible or trivial. So probably lots of the things that I've discussed today look impossible, but they are impossible until you understand. And then they become trivial. So if we replace physics with control, I believe that this is pretty much telling us the future. Okay, now, I strongly believe, and I'm a control engineer, that you have lots of discipline, IT, physics, biology, math, communications, and control is sitting somewhere in between. Control is everywhere. Your coffee machine in the morning, the electric coffee machine uses a feedback loop because you have to heat the water. Using a feedback loop because it has to make the coffee the right length. Feedback loop are in the elevator, in the air conditioning. There's hundreds of feedback loop in every computer. So control is the hidden enabling discipline of all what we see today as advances. Okay, so it's not very well known. Control doesn't have its own application. If you talk with a communication guy, the person will show you the mobile phone, and then you will say, well, you have a great achievement. If you talk with IT, they will show you a computer. So this is its natural application. Control doesn't have an application. Control has to do with math, has to do with communication, with IT, with physics, with biology, with everything, and is an enabling discipline. All right, so this is everything from me. Thank you very much.